All right, thank you everyone. Yes, so this talk, Inference as DSP, this is work that was done under the DARPA Triad program. I think it's a very interesting program, asks basically the question, hey, we have all these frameworks that do machine learning for us that operate on tensors. Can we not somehow leverage all the great software engineering that's gone into these things because they work on heterogeneous processors? Maybe not the processors that we use in wireless systems, but there's a lot of engineering in there to be able to make it work on a lot of different hardware. So we have a great team that I've been working with at Peraton and also Concurrent. And so I'm gonna try to give just an overview of some of the work. The work is still ongoing, and it's in and out of tree module to kind of give an idea of, what is another way that we can do heterogeneous compute with GNU Radio. There's been some presentations here and over many years about how can we use even GPUs is a very common one. How can we use FPGAs? There's a lot of work here. So I'm just going to kind of present another approach that this could actually go with. Okay. So what do I mean by inference as DSP? All right. So the thing that we really want with GNU Radio, we already have a great library of processing on the CPU. If you know C++ or a few other languages, you can implement things on the CPU just fine. But what I've always personally wanted with GNU Radio is to have this kind of like drop down on a GNU Radio block and be like, can I just put this particular block on this accelerator over here, or can I assign these exact resources to this block? As much as possible as a developer, I always want the most control that I can possibly get over where things execute, even down to how many clock cycles can I actually put to a particular operation. That's really nice when you're trying to accelerate things. When you're prototyping, maybe you don't care as much, but this is kind of the concept that we're going for here. Okay, so why is it actually difficult? So, this is something that people have tried for many years, and I'm not saying that I've broken through and finished it, but why is this so difficult? Well, even though there are actually many libraries out there that actually implement basic DSP operations. I mentioned some here. QSignal is one that's out. OpenCL and OpenCV have been out for quite some time. And also, there are things to even help you do it on, help you do DSP on FPGA, right? Actually, Vitis libraries is kind of a newer thing from Xilinx that helps you attempt to go from something like C or C++ down to gateware. At SRFNOC, there are some, at least there's a way for you to implement DSP and put that in that FPGA in there and get it to run in line. And there's been some other work more recently on how do I get machine learning models into the FPGA. Actually, I think there's probably more frameworks than I've actually mentioned here. How can I go from Python, right, all the way down to an actually implemented circuit, right? So these are great work, and they're making great progress. But the questions that still kind of remain unanswered by these libraries themselves is, what if I have multiple devices? I don't just have a single GPU. Or what if I have like a whole collection of FPGAs? How can I actually use that well? Usually the more resources you have, the problem becomes scheduling. How do I actually map the right work at the right time, especially if my load is dynamic, to all of these processors? And there were some good talks on that problem. How do I efficiently handle transfers? That's usually the big one. If you cannot handle the transfers well, it's almost better to not have an accelerator altogether. And the question that's always on my mind is, what is actually the best model of maintaining such a library? Because to have a library that's heterogeneous compute, you have to have a very diverse set of experts who have the time to continuously maintain these kernels. And I think this is one reason why PyTorch and TensorFlow have been successful, is because there's quite a lot of resources behind these pieces of software to continuously maintain and develop and bring kernels that have been highly optimized by a few experts to the masses, right? This was not an easy software engineering feat, and that is always going to remain the question, how can I make such a library maintainable? You need a lot of resources. So the approach here that we're taking is try to use PyTorch and TensorFlow to do the things that we do every day in the wireless signal processing world. And also, we'll use it for machine learning as well. I'm not going to focus that much on that, but because these libraries implement tensor operations, and one of the most common operations in machine learning models are convolutions. Convolutions is quite a lot of DSP, so we could try to leverage accelerated implementations of convolutions. So what we're going to do is we're going to try to integrate GNU Radio and GNU Radio Companion. Instead of having the block be implemented kind of natively in GNU Radio, what if we can offload that work to an inference server? Right? An inference server is a kind of a new piece of software that attempts to take all of the hard work of these machine learning engineers, or whatever you want to call them. They build models to do things at scale. How can I just box that up and back it by hundreds of GPUs, right? That kind of software is now becoming open source, becoming available. And so what if we just have a block that basically actuates something like that on the back end so that we get the power of all of those engineers solving the problem of scheduling in this case. And the idea here, what I'm going to show today is this out-of-tree module. The result is you write something in Python, you write a model, right? That's the machine learning idea here, but we write a model to implement DSP, and that can be implemented on multi-core CPU, so it gets multi-processed or multi-threaded, depending on which inference server you're talking about. GPU, multi-GPU, and then something called the Deep Learning Processing Unit, right? This is a special thing that shows up on the FPGA. I'll talk about that more later. Okay, so what's the architecture? So what we want to do is you want to use this very familiar development front end, right? That's GNU Radio Companion. And we want to, using that, we want to talk to the inference server. That's the lower part of that figure there. So how do we do that? You just try to make a block here. You see this is a work function if you can't actually see it. And all we do is that work function just takes the data that's inside the work function and hands it over to the inference server, whatever that might be doing. And it gets the result back, and that hands it back into the GNU Radio flow graph. Okay, so that is kind of the architecture. I'm going to break this down even further so we can understand better how this can be helpful and where it's going to hurt. I'm sure those of you who have attempted something like this may already be familiar with kind of what some of the caveats may be. So I'll first focus on Triton Inference Server. This used to be called TensorRT Server, right? Actually, NVIDIA rebranded it to Triton Server because people started to think it was just TensorFlow. But it is not just TensorFlow. It can do quite a bit more than that. And this works on CPU, GPU, and multi-GPU, right? So this is the architecture diagram you'll find on their documentation. So some of the things I want to draw your attention to is that box right there. It shows you do not have to stick with PyTorch. You can do TensorFlow. You can do actually some other ML frameworks. You can use those to implement models. And it will basically instantiate a version of the runtime that's appropriate as you import it into this inference server, and then it will use that, okay? The way this works is they supply client libraries that you can dispatch inference requests for. They work on a variety of different platforms. The other important thing here is that it doesn't have to be treated like a remote piece of software, meaning you don't have to send an HTTP request. There is a way for you to actually embed this inference server in the same process, right? And that can save you some transfer overhead if you want. And each model, the way Triton Inference Server works is it has its own scheduler to optimize the throughput of that single model. It doesn't actually do it across several models, but there are ways using other kinds of schedulers to be able to make that better. Okay, so instead of doing things inside of a GNU Radio block, because the way this was implemented, there's just one block, the actual model and all of its operations get defined elsewhere. So for Triton Inference Server, one of the things you have to do is you have to give it a configuration file, tell it where do I want this model to run, CPU, GPU, and what are the inputs and output sizes. Other than that, when you actually implement the module, you'll see actually here, this is the way you implement an FFT. I've written it here in Python. Luckily, PyTorch wrote an FFT, a native FFT recently, so you can implement it like this, and that will get compiled into something like TorchScript, and then Triton Inference Server can take inference requests with an FFT. Okay, so that's how Triton Inference Server works. Again, the cool thing here is, once you've written it once in Python, you can get a model on CPU, or it's multi-threaded CPU, and then multiple GPUs from that. Okay, the other thing here that I want to mention, this is perhaps newer. Xilinx, if you don't know how long it's been out, there's this thing called the Deep Learning Processing Unit, which is something that runs on the FPGA, runs in the programmable logic, can run alongside of other things. So this deep learning processor unit, as they call it, you can kind of think of it like a deep learning coprocessor. It actually has its own instruction set. It has has this kind of independent clock cycle, but the instructions are optimized for things that machine learning models tend to do, which again, luckily, is mostly convolutions and matrix multiplies. So that's something, and those of you who are very deep into FPGA development, the way they implement this, it's backed by DSPs. All right, so DSP slices are the things that are underlying this. The great thing, again, is that it's configurable from Python, right? You can actually decide what weights and what operations those DSPs do all the way up from Python, which is a really handy thing for us, okay? So ultimately, Xilinx provide this as a customizable IP block. You can decide how many, there's many kind of hooks and parameters that you can do, but the cool thing about the DPU is you can use this without using, I want to say, the significant Xilinx tools at all, if you don't want to, right? They actually have images where DPUs are instantiated, and you can actually just use the FPGA without, even place and route or other kinds of things. You can make use of it even at that level. Okay, so why is this special? Yeah, no place and route for a new model. You just load in new weights. It has a way to compile this thing because it's like a coprocessor. You're basically writing a program as you're actually doing a model, and that can be, again, very handy. The great thing here is it has a high amount of parallelism because with FPGAs, yeah, there's so many ways you can parallelize things on that, and you need to be aware of that. Okay, so working with the DPU, again, we're going to have this similar thing where we actually use PyTorch to define a model. That model gets compiled into something that the DPU understands, that gets instantiated on the FPGA, and then using the Xilinx runtime, you can actually, actually you don't need to touch the Xilinx runtime. They have an API that interacts with it for you, but if you want to be super efficient, you can go down deep into the weeds and mess with it a little bit more. Okay, but this is an important diagram here. On their documentation, they kind of describe how they've parallelized the DPU inside of the fabric. And so if you're familiar with 2D machine learning models, this might make more sense to you, but basically, because images are usually 3 channels, right? You can think of what this is basically saying is that if you can describe your operations as 2D convolutions that have many channels on the input and many channels on the output, then this will allow you to have highly parallelized operations inside of the DPU. So what's important here is that unlike the GPU, in order for you to use the DPU, you need to write Python knowing about this architecture. And that it's not for free that you just write a nice model and it just is parallelized. You need to write it in a way that, oh, okay, if I want to use more of the parallelism in the hardware, then I need to implement my DSP in this very specific way, right? It would be great if that could be abstracted a little bit more, but hey, you're on the FPGA, that's a great start. Okay, some caveats with the DPU that should be obvious to those of you who've dealt with FPGAs before. It's fixed point, not floating point. So you're going to be losing some information there. All of these DPUs operate with 8 bits, right? So it's not that it's 16-bit or even 32-bit. They are evolving this, so 16-bit is coming along at some point from my understanding. And that's why they have tools to go from a floating point model to a quantized model, right? And they actually have that process is configurable. You can decide, what's the best way to decide where my fixed point goes. There's many different options that they have there. But yes, these are the big caveats that you have with the DPU. It's definitely not free. Okay, so what I'm going to show you here is some throughput measurements. I'm not ready to call these things benchmarks or anything like this, right? This is just to get a taste of what can this actually do with an inference server on a CPU or on a GPU or on the DPU. Some of these implementations, I'm sure, can be optimized further from where they currently are, and maybe some of them appear faster than they might actually be, but that is, again, the work in progress that I'm working on at the moment. Okay, so first thing is the Triton Inference server. We want to be able to figure out, okay, how much overhead are we incurring with these HTTP requests? Every time I get an inference, I have to send off an HTTP request. The way I've implemented this, luckily, it doesn't actually have to copy the whole data into that HTTP request. I just put it in shared memory, and I tell the inference server, hey, the data's over there. Can you operate on it? And then tell me when you're done, and I want you to put it over here. Yeah, so that's how this works, and we want to make sure, how much overhead is that? And the way we'll analyze, how much overhead, or actually, want to say we're trying to separate that overhead from the overhead we might have from using it in GNU Radio. So I just used Perf Analyzer. This is a tool that comes with Triton Inference Server. This allows you to just take a model and then with certain parameters, just try to go as fast as you possibly can. Okay, so I ran this on a Lambda Labs box, right? It has four NVIDIA 4500 GPUs and an EPYC processor. And so this is what we get, right? One of the things that we first start with is an FFT. I ran 2 different sizes. So when you look at the left diagram here, CPU and GPU for an FFT size of 512, they operate similarly. This might be surprising, but there's highly optimized versions of the FFT out there nowadays, and they run on multiple cores. So for small enough batch sizes, actually CPU and GPU can be quite comparable for certain kinds of DSP operations. Another thing you see here is that, yeah, with multiple GPUs, for certain operations, it will scale roughly linear, but not always. Specifically, you see in the right-hand side here, the bigger the batch size, the smaller the throughput. Where is this coming from? It's because the inference server itself has a bottleneck, right? Actually, when you try to throw 1 million inferences at it, it will try to triage those things. It's going to spend all the time just trying to figure out what to do with all these requests. So it's going to slow down, right? So even these inference servers kind of need to be handled correctly in order for you to get any benefit out of that. I also did some benchmarks with convolutions with very large taps. You kind of have a similar story here with the convolution. Dot product, right? This is another very simple operation that we use in a lot of DSP. And again, what you see is that using the GPU, you get more power out of it. Multi-GPU, even more so, again, if the operations are big enough for it to benefit from that. Okay, so moving on to the last part here. I did some initial measurements on the DPU. Again, I've validated that these DPUs do what I asked them to do, but there's definitely more room to eke out even more. And in some cases, there needs to be some debugging to make sure this is exactly what I have. Okay, so basically what I had was a Korea KV260. It's a product from Xilinx, about $200. You instantiate a single DPU on here. And there are platforms that you can put multiple DPUs. So this is just one lower end DPU that we're benchmarking here. And I'm not actually counting any of the time from the PC over to that board and back. Okay, so all this is actually talking about is just how fast can this DPU operate just actuating the DPU. So what I did was this one's actually a dot product. Again, the idea here, a dot product can represent a few different things, a filter or a beamform or something like this. Let's say I had an 8-element beamformer. What the initial measurements that I have is it can handle around 60 megasamples per second throughput on a per aperture if you have 8 apertures. Okay, yes, that's the initial measurements here. And if you think about it, this thing is optimized for networks that are actually quite a bit faster than just a single dot product. So these numbers actually check out if you do at least some basic sanity checks here. Other things, I did a real only filter with 1024 taps and decimating by a factor of 64. You get around 31 megasamples per second. Using different kind of batch techniques, you can get around that much. Last one here is I did an FFT. Actually, I put an FFT on here. Actually, I implemented a DFT, so it wasn't actually the radix 2 algorithm at all. It was actually not optimized in that way. And even if you do something like this for a fairly small FFT, it's 300 megasamples per second. So to actually get the value of that throughput, you need something like a DPU and the pipe to that DPU to be big enough. The Korea board has a 1 gig interface, so you can't really get 300 megasamples per second through that kind of interface, even if it is 8-bit samples. But these are promising results on something that basically it's running on the FPGA here, highly accelerated. We instantiated it using Python. Okay. Yeah, the last thing I'll mention is that if you're interested in how these DPUs work, especially compared to GPUs, we've done our own benchmarks with vision models. If you go to Vitis AI on GitHub, they have benchmarks on all the devices that the DPU can run on, so you can get a sense for how much horsepower these things actually have for inference purposes and not just using other things. Okay, I think, yeah. So just quickly, the out of tree module, if you want to take a look at it in its current form, again, there's definitely some more work there. It's there on GitHub. If you have any questions, I will take those at this time.